Welcome back, friends. So today, as promised, we'll be looking at Lorentz group. Actually, what is the group of Lorentz transformations and the representations of that particular group. Now, before doing that, I try to revise what are a few things which we have discussed. Essentially, we first discussed what are called rotational groups, what are continuous groups, essentially, and then calculated the number of parameters associated with it, essentially. And then we talked about unitary groups, which we first we called rotation groups as orthogonal groups in 2 dimensions, in 3 dimensions, and then in n dimensions. In greater detail, we have looked at 3 dimensional rotation group. We calculate the number of parameters associated with each rotation group element, essentially, and then told saw how it can be written in terms of generators and parameters of associated with it. Then each parameter would have a generator associated. So for example, if we have 3 dimensional rotations, so you will have 1 2 rotation will have xy rotation will have one parameter associated with it, one generator associated with it. YZ rotation would have one generator and one parameter associated with it, and similarly ZX rotation would have one parameter. And then we looked at how to count the number of parameters, and then we looked at a representation theory of these rotation groups. And then we also looked at something called SU2, complex representations, complex groups, essentially, groups with complex vector spaces. So these are called unitary groups. Okay. The important point about rotation groups is they keep the length of the vector invariant, whereas in the complex sector they keep the length of the norm of the vector invariant, essentially, in the case of the complex space. So the rotations in the complex space keeps the norm of the vector invariant, and that gives you some constraints on number of parameters which you can use, essentially. We looked at the SU2 group, and we said that SU2 group has 3 generators, sigma x, sigma y, sigma z, which are the 3 Pauli matrices, and with correspondingly um, in loose terms, SU2 group is essentially isomorphic to the orthogonal group in 3 dimensions, which is SO3. So there is an SU2 SO3 isomorphism which is onto 1 1. So the number of generators of SU2 and number of generators in SU3 are equal. Not only that, every element of SU2 group can be mapped into an element in SO3. Now you can do that mapping also. You just have to multiply with sigma dot those particular vector, essentially. Okay, this mapping we have seen. Then we have looked at representation theory. We looked at representation theory in analogy with the quantum mechanics, so that we can understand everything in terms of vector spaces, essentially. And we said that the representations of SU2 are pseudo real. And then we looked at spin 1 representations, spin 2 spin half representations of SU2. Very good. I think we now covered most of the what are the prerequisites required to understand what is called as the Lorentz group, essentially. So what is Lorentz group? So today we will start with this new concept, or which is the most important concept, which is called Lorentz group. The Lorentz group, the idea is basically this, that Lorentz transformations or the set of Lorentz transformations form a group. Okay, the set of Lorentz transformations form a group. That's a basic idea, essentially, and that group is called Lorentz group. That looks okay. That looks sort of obvious, but okay. To understand this, let's start with what are Lorentz transformations. Most of you have studied Lorentz transformation in your STR course essentially. So which is a prerequisite for our course, but anyway I will recapitulate some of the important topics which we need to discuss essentially. Now Lorentz transformations are given by, let's choose a 4 vector. We'll use 4 vector notation which we have been using it. Okay, which we have been using all through anyway, but anyway just to re-express it essentially, let's just say there is t and x, or let's write x0 and x1. Essentially there is a vector which is x0. X0 is nothing but t, c is equal to 1 in our case essentially. Okay, and this is transformed by multiplying. It's a 2 by 2 matrix right now because we are only considering x0 and x1, but you can also write x2 x3, or also x1 is equal to x, x2 is equal to y, x3 is equal to z essentially. So this is just to set the notation. Essentially this gets transformed into x0 prime and x1 prime in terms of gamma, eta, and then eta gamma. Okay, I just wanted to introduce this notation just for purposes. So the first notation, I'll come what are gamma and eta essentially. Let's first define what is beta. Okay, beta is a boost essentially, or beta is V by C. Beta is defined by beta C, and gamma is equal to 1 by square root of 1 minus beta square. So this is nothing but P because C is equal to 1. This I already introduced you in the previous one of the lectures when I was introducing U boost. So I am just, but I just wanted to make this notation much more clearer because this is like recapitulating what you already know and in a better notation because okay. Then what will be eta? Eta would be, which also we introduced earlier. Eta is nothing but beta gamma. So that means this is nothing but b by root of 1 minus v square. So this is precisely we wrote, we introduced gamma eta as gamma as cos xi, and eta as okay, remember we earlier introduced cos xi is equal to gamma, sin xi is equal to eta. This is nothing but v by b square, so this is nothing but 1 minus root of 1 minus v square. This is equal to b by root of 1 minus v square. This is already we introduced this thing essentially. So this is the Lorentz transformation, a boost in xt plane essentially. So if you meaning if you don't this is now you can put instead of x and t essentially the okay, I'll come to that in a second. Okay. So this is the Lorentz transformation. Now let's go into the familiar 1 second. Now just before going further, I'll also say that gamma square minus eta square is equal to 1, which is obvious because it is gamma square is equal to 1 by 1 minus beta square, whereas eta square is equal to 1 minus 1 by v square by 1 minus beta square v square. So 1 minus v square by 1 minus v square will get it becomes 1 essentially, gamma square is equal to beta square essentially. Now the important point is now you can write it in terms of 4 dimensions. We can write in terms of 4 vectors. That's what we normally do. So to write them in terms of 4 vectors, what we do normally do is introduce the metric essentially. So the metric is equal to okay, this is what we do. But if you write it in terms of 4 components, this entire thing just becomes x0, x1, x. Are we putting upper indices or lower indices? Okay, we are putting lower indices. Sorry. So just before we introduce 4 component notation, this is something which you already know, but I am repeating it just for completeness because I want to show this forms a group. Oh, what happened? x0, x0 prime. Okay, good. x0, let me write everything in terms of lower indices. x0, x1, x2, x3, prime, 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 prime. This is equal to gamma eta, eta gamma 0 0 0 0 0 0 1 0 0 0 0 1, and then this becomes x0, x1, x2, x3. Okay, now what is this matrix doing? This matrix is multiplying. This is your Lorentz transformation. This transforming your x vector into x prime vector. That's what it is essentially. Now before, okay, so this, let me call this matrix introducing mu is equal to 0 1 2 3, which you already know essentially. So this is x mu prime is equal to lambda mu nu x nu. So this matrix represents the Lorentz transformation. So we want to do all the Lorentz transformations in 4 vectors. That's the thing. Okay, lambda mu nu is equal to okay. Now this is obvious essentially. This you can meaning I just re-express this particular thing into this particular 4 vector format essentially. This what we learn in special theory of relativity is the upper part, and the lower part is nothing but what we want to write it down essentially in this case. Now before going further, introduce the metric tensor. Now I should mention that most of this thing has been covered earlier essentially in my in the initial part when I revised special theory of relativity. Okay, I'll show you the notes in a second essentially. So this is the metric tensor. What does the metric tensor do? It takes lower indices to upper essentially. So if you have a contravariant tensor, it becomes a covariant tensor, and vice versa. Essentially, you can move it up and down. Essentially, the metric tensor moves it up and down. Now the question is, now just like rotation groups keep Lorentz transformations, meaning rotation group keeps the radius of the length of the vector invariant, and the unitary groups keep the norm of the vector invariant. What do Lorentz transformations keep invariant? Meaning, the reason I am trying to get into it, because if it forms a group, it typically should keep something invariant. Essentially, there is some symmetry transformation, so it becomes equivalent to a symmetry transformation, and this symmetry transformation keeps something invariant because we, okay. So what does it keep invariant? Okay, so the logic is that if it forms a group, it should form a uh, uh, it should it should keep something invariant, and so that's the reason what we are looking at essentially. Okay, now if you look at uh, um, okay, now what it keeps invariant, as we know, is ds square, the line element, which is x mu x mu. So the line element should always be invariant. Under Lorentz transformations, the line element should always be invariant. So what it means is that ds square is equal to x mu x mu. That means this should be equivalent to x mu prime x mu prime. Okay, this is the first thing which we see. So the Lorentz transformation should keep the line element be invariant. Now x mu prime, we know what it is from this equation. So this is equivalent x mu prime will be equivalent to having two Lorentz transformations, mu, okay, nu, then lambda mu rho, okay, x nu x rho. Okay, this is fine. So this means that if you have the line element invariant, this should be equivalent to this. Okay, this should be equivalent to this particular thing essentially. Now what does now you want to make this be equivalent to should be equivalent to what? Should be, this entire thing should be equivalent to g mu, because otherwise there is nothing which makes you some make you something. This entire thing should be equivalent to g mu. Why? Because this is length on the left hand side, this should also be length of the left hand side. So what it means, so you have conditions like so we had to be careful with the indices. So this entire thing should be equivalent on the right hand side, the matrix tensor. So that means this is, you have a condition that g mu nu lambda mu alpha lambda nu beta is equal to g alpha beta. Now let me just fix the notation here. So you can have the metric tensor on the left hand side, this will give me g mu nu. So if you write it in terms of g mu nu, okay, here in this case what happens is this is, if I re-express this one, in nu, okay, mu mu. So write everything in terms of covariant and contravariant tensors. Okay, this is alpha, this is beta, this is alpha, this is beta. Okay, this is G mu nu. So if I write everything in terms of this G mu nu into this can, okay, so this x mu nu prime is equal to, okay, lambda mu alpha. Oh, okay, I have to put carefully with this indices, these indices. Let me write it in contravariant form. Okay, this fixes the indices, so x alpha beta. So the left hand side should be G mu nu x prime mu x prime nu okay. Okay, now the indices are settled essentially. Okay, I just wrote x mu prime on the upside essentially, and the downside to be this one essentially. Now you have this relation that x mu nu prime x mu nu prime is equal to G mu nu lambda mu nu alpha lambda mu nu alpha beta. Now this entire thing should be equivalent to the metric tensor. This is what I have been trying to say, that this entire thing should be equivalent to metric tensor. This puts a very strong constraint on the Lorentz transformations essentially. Now this is like saying that you can put now if you can absorb lambda mu nu okay, so if you take, okay, G mu nu lambda mu alpha is equal to lambda mu, you can absorb the mu on both sides essentially. So this just becomes nu alpha, the repeated indices is constrained essentially, this just becomes nu alpha. Now if you do that, the condition then just becomes lambda nu alpha times lambda nu beta is equal to G alpha beta. Okay, okay, now you can raise alpha on both sides essentially, this you can do essentially. Okay, now this will make it lambda alpha nu lambda nu okay, I should be careful. Okay, lambda, okay, lambda nu alpha lambda nu beta is equal to G alpha beta. Now G alpha beta is nothing but delta alpha beta, your Kronecker delta. This will imply, if you take lambda is equal to a matrix, lambda times lambda inverse is equal to I. Now this entire point essentially is trying to show that that there is an inverse Lorentz transformation for every Lorentz transformation. For every Lorentz transformation, there exists an inverse, and then there is also exist an identity matrix. Identity. Now, why I am trying to do this shows that now, how did we get this condition? The condition is just coming from taking any vector. We have taken x mu, essentially you can take any vector and then put the condition that it should leave this line element invariant essentially. We can do this with this should be any scalar essentially, this should be any scalar. We will see another example essentially. We will see another example. This should be any scalar, and this will put constraints. Just re-expressing this, okay. I was just I introduced meaning this I rewrote it essentially as x mu nu prime into g mu nu, and g mu nu in terms of mu nu and lambda mu nu and x. This is just your Lorentz transformation. So this, as I have written it in this particular okay, there is an error in the indices here also. This should be this, and now you see, now the condition is that this entire thing, whatever appears here, should be the same as this, because x alpha x beta and this thing should be same essentially, should be equivalent to the metric tensor. So this means that you have g mu nu mu alpha and g nu alpha beta is equal to g alpha beta. That's the condition you end up having. Okay, because this should be the metric tensor, because this should be on the right hand side the length, scalar length essentially. Now this this condition I can work it out, and this condition just shows that this is nothing but the Lorentz transformation, and it can lead to the condition that the Lorentz transformation and its inverse, product of the Lorentz transformation and its inverse would lead to an identity matrix essentially. They lead to an identity matrix. Okay, this is the most important thing. Now why, okay, okay, let me stop here. Okay, let me stop here, and then I will continue again with the Lorentz transformations essentially. Okay, so the entire point of today's exercise was to show that for every Lorentz transformation there is an inverse Lorentz transformation. We just showed it in terms of this transformations of the metric. Okay, now what we will do is we will continue. We will show that there is an identity matrix, there is an inverse matrix, closure, associativity, and this is the most general form of Lorentz transformations. So we can actually say that Lorentz transformations form a group, which we will do in the next class essentially. I will stop here.